Okay, so let me start. We're looking at DNA fountain codec, and before that, I was describing the model, right? What they have used in this 2017 paper, as I mentioned. In fact, there is only one drawback still is the cost with this model, but it's a good starting point anyway. So we are looking at not this one, reddish paper, right? This paper we are looking at. So by the end of lecture today, you will see how to compute. Of course, I told you how to compute information density, right? So I'll tell you how to compute even the physical density. I'll give you the formulas. Then I'll ask you to compute it for some of the papers which are mentioned here. The physical density. So again, I'm just recalling from the last lecture. Errors are because of the following different things: DNA synthesis, imperfection, dropout, right? Degradation of DNA, sequencing errors, and so on. And homopolymer runs in GC content gives you synthesis and sequencing errors. So DNA oligo, short strand of DNA is known as DNA oligo, is divided into two classes, valid, invalid. So valid if GC content is within the range of 0.5 plus minus CGC. CGC is the controlling parameter of the GC content. And the largest homopolymer length is up to M nucleotides. So you remember last class I told you that the total length is L of the oligo, out of which I nucleotides are for the indexing, right? And we know that a homopolymer up to M nucleotide is allowed. Okay, I mean that is there. And the coding potential B is the entropy of each nucleotide in a valid sequence, and then we gave certain formulas. So basically, M, the model is controlled by 4 parameters. M, which is the homopolymer run length, any nucleotide. CG, controlling parameter for the GC content. I, the length of the index, and delta V is the dropout rate, right? While we doing the PCR. Dropout rate depends on the, how many cycles of the PCR we are doing actually. Okay, it varies over that. So these are the some, key parameters. We talked about eraser channel. So basically our storage channel is something like this. Transmitter, so synthesis of DNA oligos, message plus index of length I nucleotide. Constrained channel, so homopolymers up to M nucleotides and GC contained within the range of 0.5 plus minus CGC. Coding potential B in bits per nucleotide. And PCR and sequencing dropout rate with rate delta V, right? So this is our channel we are looking at. I already talked about a few more things here. Okay, so AX is a set of all possible transmitted DNA sequences of length L nucleotides. AY is a set of all possible received sequences. X is a random DNA sequence from AX. Y is a random DNA sequence from AY. Mutual information is HX minus HX X condition Y, where HX is the entropy. Information capacity of each oligon is C is equal to maximum over I. And the information capacity per nucleotide is CNT is equal to C divided by L. Okay. So we did these calculations and we arrived at that C nucleotide turns out to be 1 minus delta V times log 2 base size of AX divided by L. Right. So we arrived at this. Now I am going to simplify this by putting a constraint here, which is, so what is delta V? Dropout rate, AX, size of all nucleotides that are you are going to send, and L is the length of the oligos, right? So we have the homopolymer constraint. So with homopolymer constraint, the size of set of all valid code words is we denote by AXH. AX size, so you know, size A, so basically we denoted by mod or whatever you say. Actually, it's not a mod, but actually total size, indicating size of AX. AX is a set of all DNA molecules that you are going to send. AXH is with homopolymer constraint, right? So this quantity is equal to QML times 4^4L. So this is size of AX with homopolymer constraint. And QML is probability to observe up to M nucleotide homopolymer run. In a random L nucleotide sequence. If you take a random L nucleotide sequence, right, this is the probability to observe up to M nucleotide homopolymer run. Now, obviously, we need to, this is QML, right? A simpler case, I can look at a simple case here now. I can simplify this. QMEL is a quantity known as probability of not observing a run of M or more successes in L Bernoulli trials. By the way, how many of you know Bernoulli trials? Padha hoga, right? In probability. So either it is a success or failure, right? And there are of course probabilities, right? So I can say that with a success probability, P, and a failure probability, Q is equal to 1 minus P. Right. So I think if you look at any book, for example, Feller book of probability, I think you might be using Feller book. Feller Introduction to Probability. I don't know whether you, whatever book. So Feller book, if you refer, so there is a approximation, tight approximations to this quantity is given here. which I am actually writing it here. Okay. Feller book on probability, page number 301 to 303. I'm just referring these things. A tighter approximation. Tight approximation is that QMPL is approximate to beta divided by x is for L plus 1, where x is 1 plus q times p raised for m plus m plus 1 times q into p raised for m whole square, and beta is equal to 1 minus px divided by m plus 1 minus mx times q. So again, using the probability result, we have this approximation of QMPL. Okay. Q is here, by the way, 1 minus p, if you remember, right? Q is 1 minus p. So now actually, so this is given. So what they have done, they have actually, for practical purposes, they have approximated further, you know. So the distribution of observing up to m nucleotides homopolymer run as the product of 4 independent events. So these assumptions will simplify the things, right? So we have QML equivalent to QM plus 1 times T, which is 0.25, and L raised to power 4. Right? So I think now I will show you a table here. Now you can see that this is the observed rate of homopolymer mismatches versus the estimated rates from this equation, you know. So this is the estimated ones, QML, and observed ones. So you can see that for different L and M, they are almost, you know, I mean, same exactly, except in this and this very close, right? So basically, I can combine these things together actually. Combining all these equations, we have log 2 base AXH that we wanted to compute, divided by L is equal to, I'm not giving any simplifications. I mean, all the steps I am omitting here. Okay. Divided by L is equal to 2 plus 4 log 2 base beta divided by x raised for L plus 1 divided by L is equal to 2 minus 4 log 2 base x plus 4 times log of 2 beta minus log of 2 of x divided by L. Okay. For m greater than or equal to 3 and L at least 50. M is, as you know, homopolymer run size, right? So you know that 3 is allowed, right? Normally in practical purpose, right? So at least 3 should be there, right? And L is 50. 50 is the total size is 50. Normally it's 100 to 150, 200 is the depending upon which machine you are using. Okay. So further approximation is possible to this quantity. And so I'm writing that approximation now for you. Okay. So here is that log 2 base AXH divided by L is equal to 2 minus 4 times log 2 base x. So these calculations are sometimes messy, but you know, minus log base x divided by L. So this is equivalent to 2 minus 4 times log 2 base x which is equivalent to 2 minus 4 times q times p raised to power m plus 1 plus m plus 2 q square p raised to power 2m plus 2 log 2 base e. Further simplifies to 2 minus 3 log 2 base e divided by 4 raised to power m plus 1. So this is the actual value. So this, so remember we started with AX. AX is set of all possible transmitted DNA sequences of length L nucleotides. Now we put one constraint, which is homopolymer constraint, right? And we arrive at the size, approximation to the size, which is this, right? Now other constraint is GC content constraint, right? This is the homopolymer constraint. So I have to do the GC content constraint as well. So PGC is the probability that a sequence of L nucleotides is within 0.5 plus minus CGC. So PGC is the probability that a sequence of L nucleotides is within this range. Okay. So without any other constraint, PGC is nothing but 2 times phi of 2 square root of L CGC minus 1, where phi is nothing but cumulative function of a standard normal distribution. So the number of bits that can be transmitted under this constraint is, so basically I can compute log of 2 AXGC divided by L. This will be log of 2 base 4 raised to power L into GC divided by L. So I can substitute the value of PGC, which is this here. So we arrive at 2 plus log 2 base 2 times phi of 2 square root of L CGC minus 1 divided by L. Okay, so this is, so basically for one constraint, we obtain the value here. And for the second constraint, we obtain this value here. Now, both these constraints are happening together. So AX is the set of all DNA strings, right? Of length L nucleotides, oligos. Homopolymer constraints, we computed the size. GC content, we computed the size. And both are together, right? So we need to take intersection, right? Basically, we arrive at this. I guess here I can show you. So coding potential per nucleotide is B is equal to log 2 base AX divided by L, which is nothing but log 2 base AXH intersection AX GC divided by L. This is nothing but from our previous expressions log 2 base E divided by 4 is for M plus 1 minus log 2 base 2 times 5 2 square root of L TGC minus 1 divided by L. So this is a approximated formula for the coding potential. Again, I mean, you may say that is there any scope further? Yes. So here we have put homopolymer constraint can be generalized here. So of course, GC content we can keep the same expression, but for the homopolymer constraint, we can go to the conflict-free constraint, right? And you can actually recompute everything, and the formula will differ a little bit. If you want, you can do that anyway. So now, to estimate, now I have to, so basically I have this formula for coding potential. So by choosing M, CGC, and L, I can compute this coding potential. For example, if I choose CGC is equal to 0.05, M is equal to 3. As I know, M is 3 is the best thing, right? And L is equal to 150. Normally, 150 nucleotides are what machines are producing in a reasonably good shape. So then B will be in this specific situation when M is equal to 3, CGC is equal to 0.05, and L is equal to 150 nucleotides. 2 minus, you can compute these values, minus 0.003. This turns out to be 1.98 bits per nucleotide, which is close to 2. 2 is the best possible, right? As you know. Now, if I, okay, so basically now with different choice, so I would again invite you that in this formula, try to vary these values, M, GC, and so maybe you need to write a program, right? To compute this, right? And just vary these values so that you can get the corresponding coding potential. So now actually in most of the schemes that you saw, I have discussed 4 or 5 schemes, right? If I go back here, yeah. So you know you can compute. So for example, church paper, right? Goldman paper, church paper, Goldman paper, Gross paper, Robert Gross paper, right? SD, I think we have discussed here, right? No, yeah. This one and this one, at least we have talked about. Right, for these, you can compute the coding potential by choosing these values and see what is reported there, right? Are you getting the same thing? You can actually look at it, okay? From this way, you can compute the coding potential as well, right? Okay, now another important thing is index length. I have ignored index length. That also contributes to the potential, right? Suppose L prime is the remaining nucleotides available for encoding data. So L prime is equal to L minus log 2 base K divided by D actually. L prime is equal to L minus right. So the information capacity for each nucleotide will be B L prime divided by L is approximately equivalent to B minus log 2 base K divided by L. So we are multiplying the whole expression by B. So this is the only difference that you will see because of the index length. Okay. Okay. So I think that's all about coding potential. Now I am going to talk. So one thing I have not looked at the channel is the dropouts in the PCR region. So are you aware of, do you remember anything about negative binomial distribution? Have you heard of negative binomial distribution? Okay, so before going look at the dropout, I need to describe briefly about negative binomial distribution. Normally it is denoted by NB. So it's a discrete probability distribution. So you understand what is discrete probability distribution, right? So this models, I mean, there are different ways you can look at it, but this models the number of failures in a sequence of independent and identically distributed Bernoulli trials before a specified non-random number of successes. We denote the number of successes by R here. Occurs. So it's a discrete probability distribution which models the number of failures in a sequence of independent and identically distributed Bernoulli trials before a specified number of successes, right? So Bernoulli trials means each trial has two potential outcomes, success and failures, right? And each trial, the probability of success is P and the probability of failure is 1 minus P, right? I think you recall that. So we observe the sequence until a predefined number of R successes occur. Okay. So then the random number of observed failures X followed negative binomial distribution. Basically, X is nothing but what is P? P is the probability of success, and 1 minus P is the probability of failure in the Bernoulli trials, right? Okay. Just an example. Suppose we are throwing a dice and rolling a 4 on a die as a success and rolling other number as a failure. Right? So we are rolling a die. If 4 is coming, it's a success. Otherwise, it's a failure. So we can ask a question. So how many failures rolls will occur before we see fifth success? R is equal to 5. Right. This implies that the probability distribution of number of failures will be a negative binomial distribution. I will call it a negative NB, right? Okay, so I think now I can look at the dropouts. Of course, you can actually, I have not talked about, but you can compute the distribution as well, actually, But I mean, what I'm saying that you can also compute the probability mass function of the negative binomial distribution. So why it is called negative? Because while computing this, sometimes the negative binomial numbers also appear, right? That's why most likely its name is negative binomial distribution. Okay. So again, so we have to what we have to compute. So we have to consider the probability of oligos dropouts on the channel capacity. So studies have found that sequence coverage follows a negative binomial distribution. So normally we call it as negative binomial distribution with average of mu and size parameter r. Okay, so then there are different ways why we can compute. So I'm just skipping a couple of details, but I will say that the rate of the dropout turns out to be this probability mass function, which is mu divided by mu plus r raised to power r. Okay. So here is the picture, I guess. So this is the expected dropout rate as a function of the average sequencing coverage and the size parameter r. You can see the size parameter is varying and the coverage you can observe, right? So I think anyway, so I think maybe I should mention here a little bit. So normally this R actually varies from 2 to 7 actually, Okay, now I am going to talk about physical density. How to compute physical density? Physical density PD is equal to average information carried per nucleotide divided by average mass per nucleotide multiplied by average copy number multiplied by 1 plus redundancy percentage. This is the formula for physical density. Where what are these quantities here? Average mass per nucleotide is given as average molecular weight per nucleotide divided by Avogadro constant. I think you must be recalling your chemistry from 12th, right? So I'm giving you the formulas anyway, average formation carried per nucleotide. So I gave you this value here, right? Average mass per nucleotide, average copy number, and this you can find out from the specific choice. Average information carried out per nucleotide is nothing but 2 times number of nucleotides in data payload region. So nucleotide has 2 regions, payload region and the index region, right? Payload where the actual data is divided by total length. And actually, this is fixed thing. Average molecular weight is fixed. So I can just tell you what is the formula for average molecular weight. .95, and this is the constant. So basically, so now you know this thing, Avogadro constant is also fixed, right? This is fixed, this is fixed. So you have average mass per nucleotide. So then you can compute average information. So you can put this value here, this, and then you compute physical density. So obviously you want to do some calculations. So this is an interesting exercise, right? So I can give you that. Find physical density for Church model 2012, Goldman model 2013, Gross model. We already talked about these models, 2015. Morehead model 2016. Lawat model 2016. This is forward error correction if you remember. This paper, Redditch 2017 and 7. This is our paper. It's a very good exercise to compute these physical densities for each of these. So you need to basically, couple of things you already know, and few things you have to compute. So there is one way also to compute physical density by solving a nonlinear equation actually. But anyway, so here you can use these formulas to compute physical density. It's a good exercise. By the way, in this paper, supplementary material they have given the calculations as well. So if you are in doubt, you can always look at it, but it's a good practice to compute. So basically, as an engineer, if you come up with any scheme, you should know what is the physical density of that scheme, right? So 1 gram of DNA can store how much information, right? So this is something you should know how to compute, right? So that's why I'm leaving this as an exercise. And it is given in the paper. So it's not something that if you want, you can read it. In the supplementary material of the paper, it is given there, right? So I think that's all. So now in the next class, I am going to start the fountain codes. So basically, I will build with the eraser model first, and then we see how fountain codes. It's a very remarkable idea, and especially Amin Shukralahi and Michael Luby has done a lot of work. This paper uses Luby transform. So what is Luby transform? How it works? We'll talk about it. I think the next class will be probably the last class about this model actually, so where we can see how fountain codes are applied. And finally, you can see the results, right? So that is all. Then we'll talk about yin-yang model. Then we'll go further from there.